The question that I have is, what types of structural supports do we typically encounter in 2D? There are various support types out there, and there are three common ones. These are the pin or hinge support, the roller and rocker supports, and fixed support. Here are two examples of a pin support. You can see in example 1, this structural element is hinged at this support through a little pin here, right? Similar setup in example number 2. This structural element is hinged on this column through a pin there. This is the standard representation for a pin support. In details, you can see this support is very different from this one, right? But we don't really worry about the details. When it comes to structural analysis, all we are interested is the mechanics, right? So to consider the mechanics, we use the standard representation. Both of these can be represented by the same standard configuration. So this is basically an idealization of a pin support. Once we identify the support type, the next step in developing the free body diagram is to draw the forces acting on the support, right? Or what we call the support reactions. Before I proceed, let me emphasize that we've been talking about two-dimensional structures, right? So these supports also go with two-dimensional structures. So let me put the 2D in here in the title. All right, now returning to the discussion on the forces acting on a support, the first thing we want to do is to define a coordinate system, right? By default, the horizontal is our x direction and the vertical is our y direction. But it doesn't mean that this is always the best orientation for the coordinate system. In some cases, you might find the structural elements are inclined, or the support is inclined, or the dimensions are given in different directions. In cases like that, you might find a different orientation might make the calculations a little easier. So you do want to look at the problem and decide which is the best orientation to perform the calculations. So in general, there could be two forces like shown here and a moment on a given support. So you notice that I marked two forces but not the moment, right? The supports that we deal with in this course are all standard supports, and there are tables giving you the kind of forces that would act on a given support type. You can kind of memorize those and use them, right? But is there a logic behind it? The answer is yes. Supposing, say, you try to pull the structural element out of the support like shown in this first picture. If you can't pull it because the support is holding it back, then AX is not 0. So you're pulling it in the horizontal direction and you can't pull it in that direction, and therefore there is going to be a force in the same direction, horizontal direction, offered by the support. So AX in general is not 0. In this second case, you're trying to pull the structural element in the vertical direction. Pull it out of the support in the vertical direction. Can you do that? If not, AY is not 0. In the third case, can you rotate the structural element at this support A? Like you would open and close a door at the door hinge. Can you do that? If not, the moment at that particular point is not 0, because the support is now offering a resistance to the rotational movement, and therefore support is developing a moment. The first type we are considering here is like a door hinge. You could rotate the structural element freely at that support, and therefore moment is 0. That's why I did not mark any moment over here. But on a fixed support, the moment is not 0. I will come to that in a second. Here are the details for a roller or a rocker support. Here's an example of a roller support. You can see this beam is being supported on this roller. And in this example, this roller is sitting on a horizontal plane like this. But in general, the roller could be sitting on an inclined plane like shown over here. So this is our standard representation. Of course, when theta is 0, we have a horizontal plane on which the rollers are sitting. But if theta is non-zero, then we have an inclined plane. So what kind of force do we have on a roller support? Well, we have a single force, and let's call this as FA, force at point A. I mean, you could use any convenient labeling you wish. So here I'm going to call this as FA. And this FA is acting in a direction perpendicular to the plane on which the rollers are resting. The picture gives you the impression that you can take the roller off the plane without an effort. So that's not the real meaning of the roller. A roller cannot be pushed in or pulled out of the plane. So with that in mind, now we can go back and do the three tests we talked about in the earlier slide to figure out which of the three reactions will be non-zero in this case. So let's talk about the forces first. So this is a roller, so I should be able to roll it in the direction parallel to the plane, right, without an effort, and therefore there should be no force acting in the direction parallel to the plane. So that's why I didn't mark anything in that direction. But you cannot pull or push the roller on the plane, and therefore there has to be a force perpendicular to the plane. So we end up having just one force unknown at the support. Just for the purpose of applying the test that we talked about in the earlier slide, you don't want to use the horizontal and the vertical direction. Because if you do, you come up with incorrect answers. For example, can you pull the roller in the horizontal direction? The answer is no, so you're going to put an AX on that. Can you pull the roller in the vertical direction? The answer is no, so you're going to put an AY in there. So you're going to end up introducing two unknowns. Now this is incorrect for a roller. If you put two unknowns, you are introducing one too many unknowns, and later on we will see that we will not be able to solve for these unknowns. So here I have written a cautionary note for you. Do not mark two force unknowns like a pin. Alright, what about the moment? Do we have a moment at the support? Generally, rollers are connected to the structural element through a pin. So if this is what you have, you can rotate the structural element at that point effortlessly, and therefore moment is zero. Alright, now let's talk about the rocker support. The rocker support is a slight variation of the roller support, achieving basically the same thing. So here's an example of that. So here's this little beam element which is connected to this rocker support, and the rocker is sitting on this horizontal plane. You can move this beam element in the horizontal direction effortlessly, and therefore there cannot be a force in the horizontal direction, but you cannot pull it out of the plane or push it in, and therefore there has to be a force in the vertical direction. So this rocker behaves exactly like a roller when it comes to the mechanics. In other words, the type of forces that will be developing at that support. Again, in general, the rocker could be sitting on an inclined plane like this, and the force system that we have on the rocker support is identical to what we had in the roller support. Our third common type is a fixed support. Here's an example of that. You can see all these beams, right? This beam and this beam are welded together at this joint, and they are welded to this column. And this is the standard representation of a fixed support, and in this picture you see the forces acting on a fixed support. You can see I cannot move the structural element in either of the three directions we talked about earlier. I cannot pull this in the horizontal direction, therefore AX is not zero. I cannot pull this in the vertical direction, therefore AY is not zero. I cannot rotate this at point A, and therefore the moment is non-zero. You can call this either the strongest support among all the supports we talked about so far, or the most general support. Most general because the support offers all three of the possible forces, two forces and one moment. This table 5.1, kind of summarizes the supports that you typically run into in engineering disciplines like civil engineering, mechanical engineering, offshore engineering, and ocean engineering. There are 10 different types that are discussed here, including the ones that we talked about so far. That is the pin joint, the roller support, and the fixed support. So let's briefly go over this. In this first type, you are simply using a cable or a rope to hold the end of this structural element. The force acting on the structural element at that point is going to be simply the tension in the cable. So you simply have one unknown F, and that F is acting in the same direction as the direction of the cable. The second type here is similar to the first kind, But here, instead of using a cable, we are using a rigid member like a 2x4. So the primary difference is that a rigid member like a 2x4 can take both the tension and the compression. On the other hand, a cable can only carry tension. We normally neglect the weight of the link so that there's just one unknown F, and it could be tension or compression, but the analysis will tell you whether it's a tension or compression. The third kind is the standard roller that we talked about. The fourth is the rocker that we talked about. In the fifth type here, we are not using any special arrangement at the end of the structural element. The structural element has a nice round smooth end, and that end is just sitting on a plane. If the contact between the structural element and the plane is smooth, then this contact is identical to the rocker and the roller in terms of the mechanics. You simply have one force unknown, and that is acting perpendicular to the plane. Because if the contact is smooth, you can easily move that in the direction parallel to the plane effortlessly. You can also rotate the structural element effortlessly at that contact. In the sixth type, we have a roller confined in between two parallel smooth planes. So here, you cannot either pull the roller out of the plane or push it in, and therefore the force can either be in that direction or in that direction. So typically for a roller or a rocker, this is what we should assume if the details of how the roller or the rocker is constructed are not given. In this seventh type, we have a little collar that is sliding on this pipe support. In the ninth type, we have a similar arrangement. We have a collar that can slide on this little pipe support. But the difference between seventh and ninth is that in the seventh, the structural element is pinned to the collar, whereas in the ninth, the structural element is welded to the collar. So in the seventh, the structural element can slide in that direction and rotate about that point effortlessly, whereas in the ninth, it can still slide in that direction effortlessly, but you cannot rotate this. So the seventh is identical to basically a roller support, right? So you have a reaction perpendicular to the plane, whereas the ninth is a little different. You have a force, non-zero force in the direction perpendicular to this pipe, and you also have a moment because you can't rotate this freely anymore. The eighth here is the standard pin support we already talked about. The 10th here is the fixed support we already talked about. Let me make one additional comment on the pin support here. Well, you might say, well, we have two components here, Fx and Fy. Why don't we represent that as a single resultant force, right? So then you have one unknown. Since these two components are independent, the magnitude of the resultant force alone is not sufficient to represent the force. We also need the direction, right? So now you can see there are two unknowns, the magnitude and the direction, right? So you can either use this representation or this representation, but in either case, you have two unknowns. And the same thing over here. You can take these two force components and represent that as a single force in terms of a magnitude and a direction, but you are still introducing two unknowns, not just one. And here we have two unknowns too for the forces. But the moment is still there in either case. A moment is sort of independent from the forces. You cannot combine a moment with a force like we could combine the two forces and represent that as a single force.